visiting all the way from the math department to tell us about thermo-field dynamics. So the down button should work now.
So, what I would like to talk about today is started with my very old work, written more than 50 years ago, where I suggested the formulation of quantum theory in terms of positive functionals in Weyl and Clifford algebra that I called L functionals at this time. And I worked on this for several years with my students, Chutkin and Fatseev. And after that, we almost forget the stuff because we shifted to magnetic monopole source, instanton, and so on. And this probably was very understandable. And this was really very interesting things. But maybe it was a bad idea to forget it for many years. But recently I thought about scattering of solitons and corresponding quantum particles. And this mechanism that we used 50 years ago is really appropriate for this work. So I started to look at this stuff again. I found that a part of it were discovered in the 90s by Umezawa, and who gave this the name Thermo-field dynamics. And moreover, the methods that we use are really much simpler than the methods that Umezawa used, and much more transparent. But the thing that I think that really very important is the fact that scattering matrix in the formalism of all functions gives inclusive cross-sections. Not usual cross-sections, but inclusive cross-sections. And I would like to remind that inclusive cross-sections, as defined in the slide, simply is a sum of cross-sections, inclusive cross-sections of P1, P2 to Q1, Q1, Qn, is a sum of inclusive cross-sections where you have something else, anything else, and then if you are summing over all the stuff that you can, all additional stuff. So, and why this is important? Really, inclusive cross-section is the only notion that can be applied to collision of quasi-particles, in particular to thermal quasi-particles. Because if you have an equilibrium state, you really do not have stable quasi-particles. The better thing that you have some almost stable quasi-particles. And when you collide them, there is almost no hope that you will get only stable quasi-particles. You will get something else, or maybe you do not have any particle interpretation at all. You have some particles, some quasi-particles that play the role of particles. But this is not the story. So I believe that in statistical physics, the notion of inclusive cross-section is absolutely crucial. But I believe it is useful also in elementary particle stuff by many reasons. One of them is that when you collide particles, you use what you very often what we see in experiment is inclusive cross-section, because you do not see sum of products of collision. And another reason is that not every theory of elementary particles has particle interpretation. So for example, in conformal field theories, the general rule that you do not have particles, you do not have particle interpretation. But this is true not only for conformal field theories. Simply you do not know whether you have only particles at the very end. Maybe the situation is precisely the same as in statistical physics. You have any question?
No.
So, well, you definitely do not have particle interpretation. So there's something that I can say without any formulas. But now I would like to explain how to get this. What do we get? We get a diagram technique for calculation of inclusive cross-section and of scattering matrix that gives them that I call inclusive scattering matrix in the formalism of L functions. So, what I'm suggesting, look at this formula number 1, where A and A plus are creation and annihilation operators, and alpha and alpha star are simply numbers, better to say sequences of numbers. If you have creation and annihilation operators are labeled by natural numbers, or maybe creation and annihilation operators are labeled by continuous parameter. Then you have integrals functions and integrals instead of sums, sequences and sums. So you have this formula that defines L function corresponding to density matrix, and one can say basically that this L function is a generating function for correlation functions, not more than that. So, basically, you can take here as density matrix any density matrix in the representation space of canonical commutation relations. And one should say that when you have infinite number of degrees of freedom, then you have many different representations of canonical commutation relations. And this creates some problems. You can try to work in Fock space, but you can do this usually only in finite volume. If you are working in infinite volume, Fock space is not appropriate. And basically, every equilibrium state lies in its own Hilbert space. But L functions are really functions that are good for any Hilbert's representation of commutation relations. This is a real advantage.
So I think in the physics literature, is these L functionals, it looks like very much like something called the coherent state, using coherent states as a complete set of states.
This is definitely related, but they seem not quite the same, but more or less, yes, you can have more or less equivalent formulation when you introduce this decomposition in terms of coherent states. Yes, you can do this. So, now what can you do with the cell functions? And basically everything. So L functional is a functional of alpha star. It satisfies some conditions. One of them, specificity condition, that is related to functions in Weyl algebra which is generated by commutation by A star k and ak. So, what can you do with this? First of all, let me give some answers. Basically, what I'm saying, that you can define scattering matrix in the formalism of L functions. You can do this directly. but that I will talk about this at the end of next seminar. However, what I suggest in this slide, I'm suggesting simply to define scattering matrix in the language of functionals by the formula on the second line in this picture, on this slide. And what can you say here about the scattering matrix defined this way? It is pretty easy to check using this definition that inclusive cross-sections are expressed in a very simple way in terms of matrix elements of this scattering matrix. This is the first thing. Not very surprising, because you see from this formula that you have here S and S conjugate. So matrix elements of L functionals are bilinear, or better to say sesquilinear functionals of matrix elements of usual scattering matrix. So this is true also for inclusive perception.
So is the, just to make sure, see if I'm following, I mean, so I should think of S hat L sub k as you defined it there. That is the generating functional for the inclusive S matrix.
This is the generating functional. This is.
Is that correct? No.
What is LK is generating function of correlation functions of K.
Right.
This is.
Right. So I'm trying to understand how S hat is related to this inclusive cross section. So S hat is a functional on these L sub k's that depends on the alphas. And so I was guessing that this thing is the generating functional for the inclusive S matrix. Is that a correct statement?
So this is, okay, you can say it this way.
Okay.
Then the next thing, how to calculate this this matrix element of inclusive scattering matrix directly. And the procedure is as follows. You should define generalized green functions. Generalized green functions are defined here by this formula. This is, you take anti-chronological product of Heisenberg operators denoted by B, then chronological product of Heisenberg operator denoted by A. And after that, you take expectation value of this product of B and E in the state described by L function. So, for example, you can take here as L. You can take equilibrium state or ground state. Let us take ground state. So then this generalized green functions. The first statement that there is a diagram technique for calculation of them, and moreover, these green functions, these generalized green functions, they appear in Keldysh formalism of statistical physics and in Thermo-field dynamics of Umezawa. So diagram technique is there. And then the next statement is that this matrix elements of inclusive scattering matrix can be expressed in terms of on-shell values of this generalized gain function. So, yeah.
No, I'm just scratching. Sorry.
So these are basically the main statements that I would like to try to explain. And one more statement is that this diagram technique is basically the same as as in Keldysh techniques and Thermo-field dynamics. The only difference is the derivation is much, much simpler. So let me explain how to work with these L functions. So look, what can you do? You have operators on acting on density matrices. You can multiply density matrix from the left and from the right on creation and relation operators. And it is easy to define corresponding operators in L functions. This is an easy calculation. But the important thing is that scattering matrix and these operators depend on the choice of Hilbert space of representation of CCR. L functions do not depend. So here we've written formulas of this kind. So there are formulas, there are operators on L functions that correspond to operators on density matrices. And now, if you know this, so you can say that basically that you have an action, a double action of Weyl algebra on L functions. And this is precisely what happens in this in statistical physics in Keldysh and TOD. So you have this doubling of fields and doubling of creation and relation operators. So, not very surprising that now you can really get equations of motion of L functions. Nothing special. Simply you write down the equations that you have for density matrix, and you have an equation for L functions. So simply, basically, what happens? You have Hamiltonian represented in some way, and for L functions, you get this equation number 7, where you have H and H tilde that can be written in a very simple way. Equation 5 and 6. And you have some replacement of Hamiltonian, usual Hamiltonian, acting on L functionals. It is denoted here by H hat. It is equal to H minus H tilde. And I use the notations that are used in TFT because this is precisely the same equation that people write in TFT.
So, sorry, what is the B's you defined before in the previous thing, but what are the B tildes?
B tildes were also defined the previous slide.
Oh, I'm sorry, I missed.
This is, let me go back. So even slightly earlier. Okay.
so sorry.
Basically, you have 4 operators on density matrix. Multiplication by creation from the left, annihilation from the left, and the same from the right. 4 operators. And here this is B, B tilde, B, probably B plus, and B tilde plus.
So somehow in thermo-field dynamics, you are doubling the Hilbert space formally, and you're saying that the space of L functionals is equivalent to that doubled Hilbert space.
Yeah, precisely. Precisely.
Okay.
The only difference, there are 2 differences. First of all, it was written in my paper 30 years before Thermo-field dynamics.
Right.
And the second difference is what they are doing is basically some artificial construction. And what is done here is absolutely transparent. So you write this formula 1, and after that you derive everything at the moment. So, okay, I should go back. So you have the Hamiltonian, and so if you have the Hamiltonian, you can do many things, and one of them is I would like to do. I would like to consider a diabatic evolution for L functions. And what can I say? That a diabatic evolution is much simpler than in the case of standard quantum mechanics and Hilbert space. By simple reason. Really, in quantum mechanics, when you consider a diabatic evolution of stationary state, then you have a phase factor denoted here by C, which is the second line from below. But when you go to density matrix already, this phase factor disappears. And therefore, in the formalism of functionals, the statement of adiabatic theory is simple. So now, what I would like to show you is the calculation. I would like to consider Hamiltonian, free Hamiltonian. That is written and second line. And I would like to calculate equilibrium state for this Hamiltonian in the formalism function. This is simple. First of all, notice that for discrete approximation of this Hamiltonian, you can write down the equations for Gibbs state. You can write down the equations that number 9 here. One is Gibbs state, and then it is represented as some exponent of trace of the trace of exponent of Hamiltonian. And using this stuff, you can write down this equation 8 for density matrix. But after that, it is absolutely trivial to write down the equation, corresponding equation for L functions. And you see the equations, and you can solve them. And you see that L function for equilibrium state is Gaussian. It is Gaussian with some here some factor mk relates to the number of particles, as you know. But what is important for me is that mk can be taken also arbitrarily in this speech.
Question?
Yeah.
Equation 9 seems to suggest that omega k are complex.
Sorry?
Equation 9 seems to suggest that omega k is complex. Because when you take complex conjugate, because the exponent changes sign.
No, this
Commuting an operator.
omega case, what you have this. You have omega k in the Hamiltonian. It's a given number. So and if you write the equation here. Sorry, no, that's, I don't think so. I could make a mistake inside. I do not say that this is, no, but this is not related to complexity. So, so we have this stuff. And now, what we can do, we can take ADL function and go to say adiabatic evolution. So, okay, so, but after that, you can take this function L anyway, but I will take in this adiabatic evolution, I will take Gaussian function. And of course, for the adiabatics, for the adiabatic evolution, you can write down the standard diagram technique. After that, you can define adiabatic green functions, now already generalized green functions. Again, precisely in the same way as green functions are defined in this standard situation. So again, you can say that green functions can be obtained in a little bit in a different way. The usual picture, you have adiabatic green functions where really the technique is precisely the same as for adiabatic scattering matrix. Only there are only external vertices that are different. But also you can define green functions as expectation values of chronological product of some Heisenberg operators in physical vacuum. What you can do is here the formula is the same, absolutely. The only difference is that it is not necessary to take vacuum. You can take those any Gaussian functional and dress it by means of adiabatic evolution. This will be, if you started this equilibrium state of free Hamiltonian, at the end you will get a free equilibrium state of the complete Hamiltonian. So you have this new scattering matrix, new green functions. But I would like to stress these new green functions are precisely the green functions of Keldysh and TFT that I described. You have chronological and anti-chronological process. Because here, when you go from scattering matrix, from density matrix to L function, the time ordering shifts. And you will get relation of these green functions to green functions that I described. So you get a diagram technique. So you can calculate propagators.
So in which sense this is on-shelf formalism? Because you calculate the green function.
Still didn't come with this. Let me answer this question 5 minutes. What do I get is diagram technique. This for this generalized green functions, these propagators that are written here, and this is standard propagators of statistical physics. This double field formalism. Okay. What is new? So here, this is what they get here is simply another derivation of diagram techniques. It's a nice thing. I'm planning to include this in the English edition of my old book, Foundation of Quantum Field Theory. But what is new? The new thing is that this really, this green function should be used to calculate this inclusive cross-section. And to do this, first you should notice that if you take two-particle green function in this formalism, it can be expressed in terms of usual green function. And the poles, if you work in k-onic representation, then the poles of these green functions, any of them, they give edges of quasi-particles. So basically, these poles can be, of course, can be complex domain. Then the quasi-particles are not stable. This can be, of course, in the usual case also. This is basically the standard thing that you can consider scattering, for example, of neutrons. And neutrons are unstable. So therefore, basically, formally you cannot consider scattering of neutrons, but you do consider, because scattering times, collision times, is negligible with respect to lifetime of neutron. So therefore, so you still you have the notion of dispersion law of quasi-particles, and if you are not very far from the real life, then you can consider the screen functions on this much better to say energy shell, and to get inclusive sections. Did I answer the question? So this is the main thing that I wanted to discuss. But now I would like to say really a couple of words about scattering matrix, about independent definition of scattering matrix in the formalism of functions. What can you do? You can define adiabatic scattering matrix, and you can try to take limit when adiabatic parameter tends to 0. And of course, as in usual case, you do not get any limits. And all the stuff, this is because this, when you have adiabatic evolution of stationary state, of standard stationary state, then the has said this factor, the space factor that appears in Hilbert space techniques in the adiabatic evolution, it disappears. However, it doesn't disappear in the case of when you have family of states labeled by momentum, as you have in the case of particles and quasi-particles. Yeah.
Can I just ask, in this formula, you take this limit a goes to 0. There is this limit a goes to 0.
This is adiabatic parameter.
Right. There is explicit 1 over a dependence in this R. So how does it exactly cancel, or why is it regular?
Should prove. So this is basically what do you have? This really the answer to this question is as follows. When you calculate adiabatic scattering matrix, if you look at the asymptotic behavior, you will see that there is a divergent phase factor in this behavior of the adiabatic scattering. That's really very easy to understand. But I would like to have finite reading. Therefore, I introduce by hand a phase factor, a divergent phase factor, that cancels the divergent phase factor that you have in adiabatic scattering. So, and therefore, this divergent phase factor gives you, it is necessary to have finite.
Okay. But you can prove that the S hat exactly generates the factor which cancels this.
Yeah.
But there are two B's, so it's to the 1 over a square.
Yeah. This is not a rigorous proof, but it is a proof which is based basically on summation of perturbation series. But yes, there is a proof. And moreover, this is what did I talk about earlier was partially new stuff. So that's Rockefeller's formula, its applications to statistical physics. That's new. But this stuff is 15 years old. And moreover, it is really a corollary of the stuff that it is even a little bit older. Not really. But also from this time. So really, when I tried to understand quantum field theory, many years ago, when I already was an accomplished mathematician, but a beginner in physics, I tried to understand what is the definition of scattering matrix? Because no formal definition was satisfactory for me. And at this time I realized, I learned from this with my students, that you can understand what is scattering matrix in terms of adiabatic scattering matrix, and ultraviolet renormalization, of course, could not consider. But renormalization of mass and renormalization of wave functions can be understood. They appear automatically when you consider adiabatic scattering matrix. Basically, adiabatic interaction, it definitely gives you another dispersion law after this adiabatic limit. And it is a little bit more difficult to understand that the realization of wave functions also arises automatically. However, one can do this, we did this. Basically, our idea, we work in finite volume and did this both limits when volume tends to infinity and adiabatic parameter tends to zero. And what we discovered is an analog of the formula 14 in this situation. So really, you can get renormalized scattering matrix multiplying adiabatic scattering matrix by this Gaussian expressions. So the same picture is valid in the formalism of Weyl functions. Yeah. So basically, this is more or less everything that I want to say. I would like to make some announcements about the stuff that I did not say. Really, in the seminar, UMAP seminar, on Friday, May, 3rd of May, I will give a talk that has some overlaps with, not with this talk, no overlaps, but with the notion of inclusive scattering. Basically, one thing that I will explain that you can really talk about the scattering matrix in the framework of algebraic quantum field theory. In this framework, so there was a theory constructed in the relativistic case by Haag and Weyl, and continued by Araki. And it was generalized also many years ago for non-relativistic case in my paper with Fatih. But what the new thing that I hope to discuss in this seminar on 3rd of May is that the relation between inclusive scattering matrix and green functions can be derived also in this rigorous algebraic setting. Moreover, what I will do in this seminar, I will really give formulation of scattering of quantum theory, where the main object is the cone of states. So it is, in some sense, what is the theory of functions is a kind of algorithmic interpretation of this idea. And in this formalism of quantum theory based on a set of states as a primary object, this inclusive scattering matrix is really the most natural object to consider. So, one more announcement that at some moment, I don't know if there is an informal seminar about wave theory, which is an interdisciplinary seminar, where I'm planning to talk about scattering of solitons. The relation to this, it's really more about problems than about results. And the relation to my today talk is really, as I said from the very beginning, the motivation of my returning to L functions is precisely scattering of solitons that I believe is very interesting topic that I will talk today. So.
Thank you.
Are there any questions, Marcus?
So your starting point was you assumed that the Hilbert space was essentially a Fock space, right? But
No.
well,
No.
you had the Hilbert space was generated by some creation and annihilation
No,
operators.
but I have
Then I
so really
misunderstood.
the first thing that I would like to stress is the following: that if you have infinite number of degrees of freedom, there are many inequivalent representations of canonical permutation relations.
Yeah, but you assume that, I think you're assuming that the Hilbert space can be given the structure of some creation and annihilation operators that generate it. You don't have to commit yourself to one particular choice. You can make Bogoliubov transformations. See, what I'm getting at is that in conformal field theory, we don't have such a structure, as far as I understand, in a general theory. We have a different structure of the Hilbert space, right? Instead of having a natural Fock space structure, or at least the possibility of a Fock space structure, we have a local operator algebra and a representation of the conformal algebra on those. And so I'm just wondering, because you had mentioned something about generalizing to CFTs, if you could say something more about that, because I don't see how you could assume that you have even this structure for a CFT. You have a different structure that's given to you by the...
That's really, you are right. That the language of creation or annihilation operators is good not for every CFT. But basically this is not a real problem. because, so, as I have said, basically, this L function is a generating function of correlation function, basically. So basically, what you okay, you can consider something very similar for any algebra of field operators. I know.
Yeah, I mean, the algebra in the case of conformal field theories, it has its natural formulation is in position space, not momentum space, right? So somehow it's not so clear how you would get something like an inclusive scattering matrix from. I just don't see. I just wonder if you thought about it. I don't see how to do it.
First of all, there are two questions in your question. First of all, can you formulate the conformal field theory in a similar way, in terms of states, not in terms of then yes, this is basically you always can work this way. The description of space of states can be different. This is yes, this is description of space of states in conformal theory is not the same, but it is you can formulate such a description. This is not a problem. Another problem is you're talking about. You're saying whether I know how to formulate inclusive cross-section. When you explain to me what is a particle, then when they explain to you what is inclusive cross-section. In this theory, there are no particles, etc.
Right. So
This is the problem.
So
This is the problem.
okay. Well, maybe we can talk a little bit more after.
Are there any other questions? Let's thank Albert again.